You know, we usually think of language as this organic, fluid thing, right? Something we feel our way through. But what if a language could be treated like a precise computable machine? Today, we're diving into an incredible system, 2,500 years old, that did exactly that. It viewed the entire Sanskrit language as if it were a piece of code.
So, just imagine for a second. A language where every single valid word could be generated from a tiny set of components and rules. I don't just mean described after the fact, I mean built from the ground up, like a program running its code. Now this isn't some futuristic sci-fi concept. It's actually the heart of a grammatical system from way back, over 2 millennia ago.
So, who was the genius behind all of this? A grammarian named Pāṇini. What he created might just be the most complete linguistic analysis of any language ever. And it wasn't just a list of rules. Oh no, it was a full-on algorithm. A language machine for generating perfect Sanskrit.
His masterpiece is called the Ashtadhyayi. It's this incredibly compact system, only about 4,000 rules, and the real magic word here is generative. See, instead of just describing words that already exist, Pāṇini's system is an engine that can literally build any correct word from a handful of basic roots and attachments. The efficiency and logic are just on another level. And make no mistake, Pāṇini's rules aren't just vague suggestions. They are engineered with incredible precision. I love this quote because it gets right to the point. Every single rule has to be perfectly defined to do its job and only its job. This is how the system avoids conflicts and chaos, ensuring every rule has one exact function.
Okay, so you've got this ancient grammar. How in the world do you get it to run on a modern computer? Well, as researchers found out, it wasn't as simple as just typing in the 4,000 rules. First, they had to decode the truly mind-bending logic of how all these rules interact. And let me tell you, it's a system that is incredibly sophisticated and at times deeply counterintuitive.
Which brings us to one of the most fascinating and kind of weird concepts in the whole system. As it turns out, some of Pāṇini's rules are basically ghosts. They operate in a way that seems to completely defy the normal linear flow of time.
This is all thanks to something called the Asiddhatva principle, which basically means invisible. Here's how it works. In one very specific, ordered part of the grammar, the effect of one rule is considered invisible to any rule that comes before it in the list. It's like an earlier rule is looking at a past version of the word, completely ignoring a change that's already happened to decide what to do next. Let's look at an example, because it's wild.
Okay, let's see how this ghost rule works in practice. So to get to the word jahi, one rule applies and turns jahin into jahi. Simple enough. But now a second rule wants to apply, and this rule is positioned earlier in Pāṇini's ordered list. Because of that invisibility principle, this second rule doesn't see the current state, jahi. No, it sees the original state, jahin. And since the conditions for it to apply in that original state, the rule just does nothing. And that's the whole point. It brilliantly prevents an error from happening. It's a genius way to manage incredibly complex rule interactions.
Okay, here's another key principle, rule blocking. You've got general rules and you've got exceptions to those rules. To stop them from fighting with each other, Pāṇini set up a very simple hierarchy. The more specific rule always wins. It literally blocks the more general one from applying. Think of it like a specific command in a software program overriding a general default setting.
So the logic goes something like this. First, the system sees that a big, general rule could apply here, but it pauses. Before it does anything, it scans to see if there's a more specific, exceptional rule that also fits. If it finds one, boom, the exception wins, it gets executed, and the general rule, it gets blocked entirely. It never even gets a chance to run. This ensures you always get the correct, most specific outcome.
So once researchers finally cracked Pāṇini's logic, the invisibility, the blocking, they could start building some really practical tools. By translating this ancient engine into modern software, they threw open the doors to processing huge amounts of Sanskrit text automatically.
Now, a classic challenge in Sanskrit is its use of these really long compound words. I mean, look at this, Sumitra Ananda Vardhanaha. That's actually 3 separate words, all stuck together. To you and me, that might be tricky, but to a computer, that's just one long, meaningless string of letters. How could it possibly figure out what that means?
Well, you use a tool built on Pāṇini's logic, of course. A compound splitter program basically proposes every possible way to chop up that long string. Then, using Pāṇini's rules, it checks each little piece to see if it's a valid Sanskrit word.
In this case, there's only one combination that works: Sumitra, Ananda, and Vardhanaha. And just like that, the meaning is unlocked.
So, we can handle individual words, even complicated ones. The next step is understanding whole sentences. Let's take a simple one. Rama vanam gachati. This just means Rama goes to the forest. For a human, the meaning's pretty obvious. But for a computer, how does it figure out who's doing what to whom?
This is where a tool called a parser comes in. It uses a Pāṇinian concept called expectancy. The verb goes is sort of needy. It creates an expectation or a need for someone doing the going and a place to go to. So the parser looks at the word endings and, using the grammar, it correctly identifies Rama as the agent, the one doing the action, and Vanam as the object, or the destination. It perfectly maps out the hidden structure of the sentence.
All right, so now we have these incredible tools for analyzing words and sentences. This is where we can really zoom out. We can apply this Pāṇinian engine, not just to one sentence, but to entire libraries of ancient literature. And this is opening up completely new frontiers for scholars.
And just to give you a sense of the scale we're talking about, the ancient Indian epic, the Mahabharata, contains over 100,000 verses. That's nearly 2 million words. Trying to analyze that by hand is, well, it's pretty much impossible. But for a computer running on Pāṇini's logic, it's totally doable. But there's a huge problem. These texts were copied by hand for centuries and centuries, and that means you get small errors, variations, scribal choices. The result is that a simple text search, your classic Control-F, is often completely useless. The exact phrase you're looking for might not even exist in the version of the text you're searching.
Here's a perfect example. You might be searching for the two words kartum arhasi, but in the text you're looking at, those two words have been combined by a sound rule into a single word kartum arhasi. A normal search is going to find nothing. So the solution is something called approximate matching, algorithms that are smart enough to find similarities between phrases even when they aren't a perfect one-to-one match.
And this all brings us to what might be the most profound conclusion of all. Pāṇini's system isn't just some historical curiosity for analyzing Sanskrit. Its underlying logic, this idea of language as a computable system, has absolutely stunning relevance for us today.
Right at the very beginning of his work, Pāṇini lays out this table, the Shiva Sutras. Now, it looks like just a list of sounds, but it is actually a brilliant tool for data compression. Pāṇini arranged the sounds in such a clever way that he could refer to huge groups of them with a simple shorthand. For instance, the shorthand a-ech refers to every single vowel, from the very first a all the way to the marker ech. It's an unbelievably concise way to define groups of sounds.
Okay, now here is where it gets truly amazing. Not too long ago, some linguists decided to test just how universal this 2,500-year-old technique was. They had a wild idea. What if we tried to apply it to a completely different, unrelated language? So they took Pāṇini's method and used it to describe the sounds of modern German.
And the result was just stunning. See, the standard modern method for this uses a system of what are called features. But what the researchers found was that Pāṇini's ancient technique, his pratyaharas, actually performed better. It was more efficient, more elegant, and more descriptive than the modern approach. Pāṇini's 2,500-year-old code had just beaten its modern equivalent.
Pāṇini's grammar is proof that ancient thinkers weren't just philosophers. They were systems engineers of the absolute highest order. It shows us that this rigorous, algorithmic way of looking at the world isn't some new invention. And that leaves us with a pretty fascinating question, doesn't it? What other ancient algorithms, for logic, for music, maybe even for consciousness itself, are just lying dormant in old texts, waiting for us to rediscover them?